try a new example. We're trying to find a UMP test. We want a UMP test for this situation over here where we have the hypothesis or the null hypothesis that our unknown parameter p is less than 0. This should be 0.1. That makes more sense. Should be less than 0.1. And our alternative hypothesis is that it is greater than 0.1. Now, UMP tests and monotone likelihood ratios go hand in hand. So recall that we have a increasing monotone likelihood ratio as a function of y, which was the sum of our xi's. We saw that on a previous video. Now, if we have a monotone likely or an increasing monotone likelihood ratio as a function of our xi's, so we have this term y, that's our statistic, and we have this set of hypotheses, we can use the theorem that we've learned already, which is up here. So this set of hypotheses, and we have increasing, and we know it's increasing as a function of t, but for us it's y. Then a UMP test is going to have this form where y is going to be strictly greater than or equal to some value c. So I know that we are going to have that form, or the UMP test will be of that form. So we're going to reject h naught for y greater than or equal to c, and we'll fail to reject if it's less than c. But we still have to figure out what c is, and we want to pick c so it has a specific alpha level. So suppose we desire a alpha level of alpha equals 0.1. So we desire a test with a type 1 error rate no more than 0.1. So we need a c such that the probability we reject h naught given h naught is true is less than or equal to 0.1, which is the same as saying the probability that y is greater than or equal to c, given that our parameter is equal to 0.1 is less than or equal to 0.1. So we don't want it to be any larger than that. Now, I just used the plug-in method for this situation to figure out what this should be. So I have all these, so let's say n equals 8. And I've gotten all these values for x's and their associated probabilities for these x's. I rounded to 4 decimal points, and yet when I did 4 decimal points for 6, 7, 8, it was 0.0000. It was still 4 decimal places, so I just did 0 to save space, but it was at least 4 decimal points, if not more, for all of these situations over here, 6, 7, and 8. So I just left it 0 for ease of writing. And then, so this is the probability of their individual values using the binomial distribution, because the sum of Bernoulli's is a binomial. And then I have this probability, so probability that x is greater than or equal to these little x's over here, to get an idea of what this probability would be. And this is all using our null value at 0.1. So this is the probability that x is greater than or equal to 8, probability x is greater than or equal to 5, probability x is greater than or equal to 4, and so on. And we see that the largest value c we could have without violating this, without going over 0.1, is this one over here. Because as soon as we do the probability that x is greater than or equal to 2, then we are over this threshold here. So we're over the type 1 error rate we're trying to stay under. So the best c we can get is c equals 3. Now, what if you wanted a test that was exactly 0.1? There is a twist that we can do. So let's start a new page for this. It's a randomization sort of feature that we can add to a test. To get exact 0.1, use randomization. Now, this is a tool that most people don't really use in the real world, but it is absolutely statistically valid, and it will help us get to that desired significance level. So, how randomization works is, okay, well, we know that the probability that our statistic y, which I denoted just a big X over here, but our statistic y is greater than or equal to c is 0.0381. What about 2? Well, we can use randomization for if we get a 2, where sometimes we reject and sometimes we fail to reject. So we're going to have this special case where we'll use a randomization procedure to sometimes reject if we have 2 and to sometimes not reject if we have 2. So it will randomly choose whether to reject or not reject so we get our desired alpha level. How do we do that? So if x equals 2, we will reject h naught with probability theta. And we'll solve for theta in just a minute. So we're going to reject h naught with probability theta. So we're going to imagine we have this special coin that will reject h naught about theta % of the time. And then we'll fail to reject otherwise. So fail to reject h naught, I'm going to say with probability 1 minus theta. So how do we find theta? Well, we want the probability we reject h naught given h naught true. With this system of this special randomization tool, this ends up being equal to the probability that y, our statistic, is greater than or equal to 3 given p equals 0.1 plus theta times the probability y equals 2 given p equals 0.1. And we're going to set it equal to 0.1. Now we know this probability over here. We found it with our table, 0.381. We don't know theta. We have to solve for it. And we also know this probability here also from our table, which is 0.1488. 0.1. Now just solving for this expression, we get theta is equal, or I should say approximately equal, to 0.4160. So we had a magical coin that landed on heads, let's say about 42% of the time, and landed on tails on the other percent. Then the times that it would land on heads, so pretend that you have observed 2. If you land on heads, you would reject, and if you landed on the tails, you would fail to reject the null. Now again, this procedure is not typically used in the real world, but it is a way that we can get our exact alpha level.